Excellent. Are you seeing my laser pointer?
Yes.
Okay, then I'm going to start the presentation. Good morning, afternoon, or evening, depending on where you are. I'm going to speak today about neural networks for transient modeling of circuits. I want to start by looking at some well-known examples of circuit behavioral models. First one is the IBIS model. That stands for Input-Output Buffer Information System. And the standard IBIS model, or the analog front-end model, consists of some passive elements that represent the package, and then lookup tables that represent the transmit and receiver circuits. Now, these models are of limited accuracy. They can't reflect changes in the operating conditions. Now, the equalizer can be represented as an AMI model. That's an algorithmic model, and it cannot be used for transient simulation. Despite any limitations, IBIS models are used widely because they protect IP, intellectual property. They're also faster to simulate than a transistor level netlist. Another well-known example are gate timing models. These are used very extensively to verify a digital design. You can check for setup and hold time violations through those timing simulations. But again, this is not a SPICE transient simulation. It won't capture effects such as crosstalk. Nevertheless, timing simulation is used very extensively because it is so much faster than a transistor level SPICE simulation. So the question I want to explore today is whether we can perform high fidelity transient simulation using behavioral models that obscure design details, that is, that protect IP and that are faster to simulate than a transistor level netlist. An obvious choice for that model structure is the neural network with its very flexible representational capabilities. And in fact, there have been some prior works in which people used feed-forward neural networks to create transient models of a circuit. The inputs to those models are the input signals for the circuit at the current time point, as well as samples of the input signals at some previous time points. And that's necessary because we all know that the output of a circuit isn't only a function of the instantaneous input signals. But with that in mind, we realize it would be more appropriate to use a model in which the concept of memory is intrinsic to the model structure itself. And that may be the NARCS model. Let's see, that stands for nonlinear autoregressive with exogenous input model. And of course, for the purpose of this talk, the nonlinear block of the NARCS model will be some sort of feed-forward neural network. Now, the NARCS models represent the state of the system as a function of the current input and the prior state or the prior output of the system. And that reflects what we understand about circuits. We know that the stored charge or the magnetic flux in a circuit can't change instantly. So these NARCS models can be formulated to represent the transfer characteristics of the circuit. That is, they may represent the output voltage as a function of the input voltage. I refer to those sort of models as controlled source models, as in voltage controlled voltage source. Now, those models have a significant limitation in that they don't reflect loading effects. We all know that the instantaneous output voltage from a circuit is not only a function of the voltage at the input ports, it's also a function of the load impedance. And to capture those sort of loading effects, we need to instead create what I call true IV models. A true IV model will represent each of the port currents as a function of the port voltages. And indeed, we can create IV-type NARCS models. When you're learning such a model, it's recommended to use training data that were generated with a variety of different sources and loads, and that's to ensure that your model will generalize well over a range of different load conditions. However, all of these models have one overarching shortcoming, and that's they are discrete time, fixed time step models. And that means they can't be used with a general purpose commercial circuit simulator, which of course does an adaptive time step transient analysis. And so we're going to need to look at continuous time behavioral models. Now we can develop or design a continuous time model that is specifically targeted to one circuit and one application. But I'm going to claim that it's better if we use a model that is generally applicable to many different kinds of circuits. And that's going to be the recurrent neural network. In fact, it can be shown theoretically that the recurrent neural network, or RNN, can represent any nonlinear dynamical system that is described by first-order ODEs. And that means it can represent most circuits. I mean, consider what the model, what the circuit model is that we normally simulate when we run SPICE. SPICE solves a system of equations that consist of first-order ODEs and algebraic expressions. So it makes sense that the RNN is suitable for circuit modeling. And in fact, we've been able to apply it successfully to amplifiers, logic gates, and flip-flops, among other circuits. Now, I show here in the middle of the page the general form of the RNN model equations. U represents the inputs to the model. X is the state or the internal state of the system, and Y are the outputs of the model. Theta F and theta G are the model parameters. The function F is a feed-forward neural network. The function G is a linear or affine function. So when you're using a continuous time RNN model, there are a few things you need to be aware of. The first is that the stability properties of your model should reflect the physical hardware that the model represents. And today, I'm only going to address the modeling of stable circuits. I'm not addressing oscillator circuits at all. And that means that we need to impose some conditions on the dynamics of this model to ensure that it is stable. The other consideration is that we're going to be evaluating our model using numerical integration, and the method we use will affect the accuracy of those calculations. All right, so given all of that background, it may be a bit surprising that there have been very few works on using continuous time RNN models to represent circuits. One of those very few prior works only created what I call quasi CT continuous time RNN models. In that work by Zai-Chen Chen, he learned or trained a discrete time RNN model, but then he used the forward Euler method to create a continuous time approximation of that discrete time model. However, Cao et al., they actually have demonstrated true continuous time RNN models of circuits, which means during training, they used an ODE solver to evaluate their model. And that is the approach we will be I'll be focusing on during this presentation. So after you train your model, presumably you want to use it for circuit simulation. And that means you need to present the model in a form that can be interpreted by your circuit simulator. For that purpose, we recommend implementing the final model in Verilog A, because Verilog A models are accepted as input by all the major commercial circuit simulators, including HSpice, Spectre, and ADS. What I have shown here on the left of the screen is a schematic representation of a one-port RNN model. These current sources solve for function or implement function F, which, as shown here, is the state equation for the system. Sigma represents the nonlinear activation function. We use tangent H in this work, and the little n subscript indicates that there are n neurons in the model, or that we have an n-dimensional state variable. Now, what's worth noticing is the number of nodes in this circuit is equal to the dimension of the state variable x. All right, so let's segue into a quick example. We learned a CTRNN model of this 9-stage inverter chain. We then implemented the model in Verilog A and tested the model by simulating it in HSpice using a variety of different sources and loads. Some sample results are shown here on the slide. Now, what's important to note is that when the circuit is being simulated by, say, HSpice, that simulator is simultaneously solving for both the port voltages and the port currents, though I've only plotted voltage here. So we have two sets of results for V1 and V2. One set of results are obtained by simulating the transistor level netlist. The other set of results are obtained by simulating the RNN, and you could see the two sets of results are virtually indistinguishable, showing that the RNN has very well learned the dynamics of this circuit. All right, so I've sketched out a very rosy picture, and you might wonder why, everyone and her sister aren't yet using these models for transient simulation. Well, there's some technical hurdles that have to be overcome, and we'll discuss those next. All right, one issue is that even though we are learning a continuous time model, the training data are in discrete time with some time step I'll refer to as H. When we simulate that learned model using our SPICE type simulator, there'll be adaptive times. It's an adaptive time step simulation, and there may be instances at which the simulator uses a time step that is much less than H. Under those circumstances, the accuracy of the model tends to be compromised. I show one particular example here. We learned a model of a flip-flop. The validation error was 1.5%, so very good. Then we implement the model in Verilog A. We simulate it with a SPICE simulator, and you could see the error is now significantly larger, and the error metric used here is the normalized root mean square error. So how do we how do we limit the error that is induced when we port our model to Verilog A? Well, might seem logical to simply use a training data set that has a smaller time step, so reduce the value of H. That's generally not feasible, because if you make H very small, you will probably run into vanishing gradient problems during training. Another solution is to use a higher order ODE solver during training, so as to better learn the dynamics of your system. And that, in fact, probably is the right solution. There is, however, one problem. RNN models are normally trained using back propagation through time. And if we're using a high order solver, the memory requirements and time needed for back propagation through time become prohibitively large. And I'll explain why. I'll go into some details on that on my next slide. But first, let me point you towards a possible solution. There was a paper at the 2018 NeurIPS conference on neural ODEs. Neural ODEs essentially are continuous time RNNs. And in that paper, the authors showed that we can address this training problem by using the adjoint sensitivity method rather than back propagation through time, BPTT. Now, this paper, on the neural ODE, it actually won the Best Paper Award at the conference. So it got a lot of attention. What's actually rather interesting is 15 years ago, when Sal was using continuous time RNNs to model circuits, he also was using the adjoint method. All right, so let's look at, BPTT backprop for a moment to understand why it can cause problems if we use a high order solver. So at the top of the page, I have the model equations written out. So we have our state equation, the output equation, and then we have a parameter vector theta, which contains all of the model parameters. Now we optimize or train this model using stochastic gradient descent. Our loss function is mean square error, and we update the parameters based on the gradient of the loss function and some learning rate parameter R. So let's, look at a particular example. Let's say that A11 is one of the entries in parameter matrix WR, which you can see up here in the model equation. So we need to take the gradient of the loss function with respect to A11, and we're going to use the chain rule for that. So now let's focus on this last term in the product. That is the derivative of the state variable at the current time point t sub I. However, x of I, the state of the system at the current time point, is a function of the state at the previous time point, dxi minus 1. And the state of the system at the previous time point is a function of the state variable, one instance further back in time. So to calculate this derivative, dxi dA11, we need to make use of all the derivatives going back in time all the way to time equals 0. And that's why this is called BPTT, back propagation through time. So if we're using the conventional method, which is BPTT, to train our recurrent neural network, we need to store the state variables, the output, and the various derivatives at all of the time points. And that means the amount of memory we need is going to scale linearly with the number of time points. While high order ODE solvers tend to use a very small time step, which means we're going to have a large number of time points. If we instead train our model using the adjoint method, we will find the gradient of the loss function by solving another ODE called the adjoint ODE. And so it might seem that we've solved all the problems and we can move on. However, we need the solution of this adjoint ODE to be very accurate so that we have a correct value for this gradient. Otherwise, if we don't have an accurate value for this gradient, it will take our optimizer much longer to finally find a good fitting model. And that means we may need to solve the adjoint ODE using a high order solver, which is going to compromise the computational efficiency that we obtained in the first place by switching to the adjoint method. So, again, because that neural ODE paper received a lot of attention, there have been a lot of researchers who are now working to try to address the training issues. And I've taken some results from one such work cited here on the slide. So what the authors did is they compared the memory cost and the depth of the computation graph for BPTT and the adjoint method. And the most notable thing is that the adjoint method requires much less memory than BPTT, or in fact, orders of magnitude less. However, the amount of time it takes to finally converge to an accurate solution is not that much less when we use BPTT, at least in this one particular example. So what the authors did is developed a new technique called the checkpoint adjoint technique, where they make use of some of the information from the forward evaluation of the state equation. And they use that for the backward pass where they're solving the adjoint ODE to enhance accuracy. By enhancing accuracy, they reduce training time, as you can see quite dramatically in this example, at the expense of somewhat more higher memory requirements than the adjoint method, but still much less memory requirement than for BPTT. So one problem has perhaps been addressed, but what other hurdles do we encounter? So let's focus for a moment on multi-port circuits. If my circuit has n ports, my RNN model of that circuit will have n inputs and n outputs. And if that number n is bigger than about 4, it can be very cumbersome to generate the necessary training data. Let me give a little example. This represents a 16-bit adder circuit. There are 64K different digital inputs that can appear at the input to the circuit. And each of those 64K different digital inputs should appear somewhere in the transient waveforms used for model training. And I certainly don't want to be responsible for putting that training set together, and probably neither do you. So let me suggest a different modeling approach. What if we instead learned the model of a 4-bit adder, and then we represented this circuit as the interconnection of 4 4-bit adders? That approach would address our training problem and is a very promising approach, provided that the interconnections between those models do not introduce a stability problem. And so that's what I want to focus on next, is the stability of these behavioral RNN models. So I've written again the state equation at the top of the page. And if we're modeling a stable circuit, the model itself should be gas, globally asymptotically stable. That means that for some constant input, the state of the system should converge to some equilibrium state. So what we've written here is a sufficient condition for stability. This model will be stable if there exists some positive diagonal matrix denoted D that satisfies this matrix inequality. You see D appears in the inequality, and the weight matrix WR also appears in the inequality. It actually can be very challenging to establish the existence or non-existence of some matrix D, given some candidate parameter matrix WR. So to address that challenge, in the prior works, the researchers just set D equal to the identity matrix. Then this inequality reduces to the one shown here. And Sao used this as a constraint when he optimized the model equation. However, that is a highly restrictive condition, and it limits the parameter space for your model, potentially compromising the ultimate goodness of fit that your model can obtain. And so I want to suggest a different and better approach to learning a stable model. For the parameter matrix WR, we substitute this product. It's the diagonal D matrix, an m by n parameter matrix W, and then this scalar term 1 divided by 1 plus rho, where rho is a scalar number greater than or equal to 0. Now, there is a typo in the paper. The paper says rho greater than 0. This condition is correct, rho greater than or equal to 0. So first thing I want you to notice is that this stability matrix, D, appears explicitly in our model equation now, or in our state equation, and this is the equation that we optimize during training. We do this with this matrix inequality imposed as a constraint. Some of the details of the algorithm can be found in the paper, but suffice to say, we jointly learn the entries of D and the RNN model parameters. And the entries of D are the parameters of the Lyapunov stability function for our system. All right, so let me show you some sample results. We learned the model of a continuous time linear equalizer circuit. We did this twice with just normal learning algorithm, and then with stability constrained learning algorithm. And across training runs, we consistently find or achieve lower validation loss when we apply the stability constraint. So it's as if this constraint is guiding the optimizer towards an accurate model of the system. All right, but that doesn't address all of our concerns regarding stability. Presumably, we want to take the models we have of the various circuit blocks and combine those together to create a system model. And even if those individual component models are stable, there's no guarantee that the overall model of our system will be stable, because there will be feedback, or there may be feedback between the various components. What we're specifically concerned about is feedback between an RNN model of a circuit and the circuit sources and loads. I have a very simple example shown here. Say we have a one-port RNN model connected to a voltage source, and the output impedance of the voltage source is represented by this R and this C, this resistor and this capacitor. The input to the R and N, U, will be the port voltage. The output from the R and N, Y, will be the current flowing into the port. Model equations are shown here. We can solve Kirchhoff's current law to obtain an expression for the rate of change of the input. So du dt at the input, and we see that is a function of g of x, the R and N model output. So the input to the R and N depends on the output from the R and N. That's feedback. And again, once you have feedback, there's a chance that your model may be unstable. So if we have a model of this form, which is what we've been working with, and we optimize that model such that it is globally asymptotically stable, then that model will also be ISS, input to state stable. That means that a bounded input produces a bounded state. Now, if all of the elements of our modeled system are ISS, the entire system is not necessarily ISS, but we may be able to apply small gain type conditions to check if the entire system is stable. And that's work in progress right now. But if we're successful in that endeavor, we will be able to model that 16-bit adder as the stable interconnection of 4 4-bit adders. But again, this is a major research challenge that has to be addressed before these behavioral models can be used for generic circuit modeling purposes. All right, another issue I want to address is computational efficiency. If we need to increase the representational capability of our RNN model, we can do that by increasing the state dimension n. But remember, I showed you earlier that the number of nodes in our circuit is equal to n. So that means if I make n larger, my circuit simulation time will also increase. There is another way that I can increase the representational capability of the RNN without increasing the state dimension. And that is by adding additional layers to the feed-forward neural network portion of our model. So I show a specific example here in which we have added one additional linear layer to our feed-forward neural network. And while the state dimension is n, the number of neurons in this model is L, where L presumably is larger than n. So here, this is work in progress, but some preliminary results are shown here. We learned the model of a common source amplifier using the basic RNN and then the RNN with one additional linear layer. And indeed, the second version was the second model was a bit faster to simulate, 13% faster in this example. That's not a huge amount, but this particular circuit doesn't have very complex dynamics, and we would anticipate that a larger circuit with more complicated dynamics, that we might obtain even greater execution time savings by using the deeper feed-forward neural network in such cases. All right, so finally, the last part of my talk, I want to briefly address what I call augmented CT-RNN, continuous time RNN. In principle, the model parameters for RNN don't have to be constant numbers. For example, the model parameters could be functions of use conditions and operating time. In that case, the resultant model could represent the effects of circuit aging, or the RNN model parameters could be sampled from a statistical distribution, and in that case, the RNN model could represent the effects of process variations. So quickly show you how we've addressed circuit modeling, how we model circuit aging using RNNs. We represent the effects of aging by as a perturbation of the RNN model parameters. We denote those perturbations as delta theta. We have this sort of offline first part model, which calculates delta theta as a function of the stress waveform and the total operating time. Then we create an RNN model in which the parameter set is equal to the time zero model parameters plus the delta thetas. And we use that model of the age circuit for our SPICE circuit simulations. Just one quick example shown here. This is an IQ clock generator circuit. It's very well known that this has a reliability problem if it's put into standby mode for a long time, because in standby mode, the in-phase and quadrature clock paths experience very different amounts of BTI stress. And that's captured in the simulation shown here, where we show the output of the QN clock path after 10 years of continual operation and 10 years sitting in standby. And you see there's two sets of results, and each set of results has two simulations, one using the netlist and cadence rel expert, and one using the RNN model, and the RNN model and rel expert provide identical results. All right, so what about process variations? Here we represent process variations again by perturbing our RNN model parameters. We sample those parameters from an underlying statistical distribution. And so for each instantiation of the circuit, we sample the distribution and obtain a set of RNN model parameters. And here's an example. So again, it's that 9-stage inverter chain example. And we simulated 100 instances of that circuit. First, by doing Monte Carlo sampling of the PDK models. And second, by sampling from the stochastic RNN model. And, you know, the two sets of the results look fairly comparable. So again, this is another very promising approach to efficient circuit modeling. All right, let me wrap up. In principle, an RNN can be used as an IP obscuring transient model of a nonlinear circuit. However, in practice, training challenges have prevented the widespread adoption of those models. We saw that the amount of required training data increases exponentially with the number of circuit ports. We saw that prior techniques for learning stable models overly constrain the model parameter space. And we think we can address both of these problems by jointly learning the Lyapunov function parameters and the RNN model parameters. Our remaining task is to provide stability guarantees at the system level. And with that, let me thank our research sponsors, which are the industry members of CAMEL. Let me thank two of our friends at Intel for their help with the aging simulations. And most of all, let me thank my co-authors, especially the two student authors, Jie Shang and Alan Yang, As you can imagine, they did all the real work that I've presented to you today. And any questions that you have, you can email any of us, and we'll be happy to address those. And with that, I am finished. Thank you.
So thank you very much for very interesting talk. And we have time for a few questions. Okay, I see that people are probably tired from the long day, so no questions. So thank you very much.
Avi, there is a question, I think, in the chat.
Oh, yes. There is a question in the chat. So the question is, do you see it feasible to extend this application to transient noise analysis, which is typically resource intensive, like stochastic RNN? Perhaps extending it in handling stochastic DE modeling, the noise in time domain. Interestingly, I have not had much success finding any MLDL related application on this area.
Okay, it's a very interesting question. It's not something we've done yet, so I can't say, oh, this would definitely work. But given that Daniel wants to do a time domain analysis, it is certainly feasible, and it's worth investigating. So Daniel, I'd be happy to continue that conversation with you offline.
Okay. So again, thank you for the talk, and for all the audience that stayed here all day, and you're welcome to join the social